Assalamualaikum dear students. In this video we are going to learn simplex method to solve LPP, and this is an analytical method to solve linear programming models. So first of all, let's go through a few definitions. A basic solution is an augmented corner point solution, and it has following properties. Since we are going to use this term again and again, so let's have look at few properties of basic solution. So in the problem, each variable is designated as either a non-basic variable or a basic variable. Non-basic variable are set to 0. The number of basic variables is always equal to the number of functional constraints. Therefore, the number of non-basic variables equals the number of variables minus the number of functional constraints. And the values of basic variables are obtained as simultaneous solution of the system of equations, which we actually got from the constraints in equation form. If the basic variables satisfy the non-negativity constraints, the basic solution is called basic feasible solution. So let's learn the method with the help of this example. In this example, we have to maximize this function, and this function is called objective function. Z is equal to 3x1 plus 5x2. This is called objective function. And these are the constraints. So subject to these constraints, we have to find the optimal value, that is maximum value of this function. So constraints are the inequality of the form less equal. So all the constraints, all the functional constraints are the inequalities of this form. So first of all, in order to initialize the process of simplex method, first of all, we have to convert this system into an equation form. So let's do that. Corresponding equation to objective function is this: z minus 3x1 minus 5x2 is equal to 0, whereas we have this inequality x1 is less or equal to 4. Now since left hand side is less than the right hand side, so in order to make it equation, we have to add some positive number on the left hand side. So let that variable be s1. This is a non-negative variable, and this is called slack variable. From second inequality, again this is less equal inequality, so we have to add another slack variable to make it an equation. 2x2 plus s2 is equal to 12, so this is the second slack variable. And in third inequality, we can write 3x1 plus 2x2 plus s3, this is a slack variable, is equal to 18. So this is the equation form of this system, and all the variables involved in this system are non-negative. So this is the non-negativity constraints. So our functional constraints are these three. So as we learned in previous slides, that the number of basic variables is equal to the number of constraints. So in this problem, number of basic variables must be 3. So initial basic feasible solution would be these slack variables s1, s2 and s3. So let's see how it works. So we have this equation form. First of all, we have to form the initial table for this, for the simplex method. So this is the initial table. Actually, this the columns dedicated to the coefficients, these columns dedicated to the coefficients involved in the system, that is x1, x2, s1, s2, s3. And this leftmost column is for basic variable. So we are going to write, this is this row is 0, and we are going to write all the basic variables in the column. And this column, rightmost column, is for right hand side of these equations. Okay, this is also called a solution column. And remember, you have to write all slack variables in last 3 columns. Since in this case we have 3 slack variables, we have 3 basic variables, so these last 3 columns are dedicated to these slack variables. So non-basic variables are written initially in initial columns, and then these slack variables are written in the last columns. So let's fill the table, and we are going to fill this table by the coefficients of these variables in each equation. Okay, so let's see how to do that. So first of all, let's write 0, z, and coefficient of x1 in 0 is -3, coefficient of x2 in 0 is -5, coefficient of s1 is 0, so 0, coefficient of s2 is also 0, so we'll write 0 here, coefficient of s3 is also 0, so we are going to write 0 here. So right hand side of this equation is 0, so we'll be writing 0 here. So this is how 0 is completed. Now next, this is the first constraint equation associated to first constraint. So again, we are going to follow the process. So this is S1 row. Coefficient of x1 is 1. Coefficient of x2 is 0 because x2 is not present in this equation, so 0. Coefficient of x1 is S1 is 1 and S2, S3 are 0. And right hand side of the equation is 4, so we are going to write 4 here. So S2 equation, similarly we can write S2 equation. So coefficient of x1 here is 0 because there is no term with x1. So 0, 2, and since S1 is not present, so 0 S1 and S2 is 1, and coefficient of S3 is again 0, and right hand side is 12. All right. So in similar fashion, we can write the third equation, that is the S3 equation. So coefficient of x1 is 3, coefficient of x2 is 2, and S1, S2 is 0, and coefficient of S1. Now you can observe here in last columns that you have identity matrix formed by these coefficients. This is also important to note because it has significance. Okay, let's find out the next level of basic solution. So for this, we have to test optimality first of all. So in order to test the optimality in maximization problem, this table is called optimal table if every coefficient in 0, I'm talking about coefficients only, if every coefficient in 0 is non-negative, then the solution is optimal. The table is called optimal table. But in case of minimization problem, if all the coefficients in 0 are positive or 0, then the problem has optimal solution, and we have the optimal value of objective function. And if we do not have optimal solution, then we have to do an iterative process. So how to do that? For this, we have to determine the entering basic variable. Okay. So initially we have these three basic variables, since our solution is not optimal because we can see the negative coefficients in 0. So we have to make any of these non-basic variables a basic variable, right? So in order to determine entering basic variable, the entering basic variable would be the basic variable, non-basic variable with most negative coefficient. That is in this case x2, because -5 is more negative than -3. Okay, so this is the entering variable, and that will enter as basic variable. So as we learned before, that number of basic variables is always equal to the number of functional constraints. So if we add this in the list of basic variables, then one of the basic variable will have to leave the basic variables. Okay, so and that will become the non-basic variable. So in order to determine that, we'll mark this column as a pivot column. Okay, pivot column. And then find out the ratio of these entries in solution column to the corresponding entry in the pivot column. So let's find out the ratio. This is 4 over 0, this is 12 over 2, and this is 18 over 2. So 4 over 0 infinite, we are going to neglect. We are not going to choose infinite one or negative ones. So this is equal to 6 and this is equal to 9. So leading variable would be the variable whose ratio is least positive. Okay, least positive. So in this case, we have 6, which is least positive among all these. So S2 will leave the basic solution. And X2 will enter as a basic variable. Okay. Now, in order to uh, find out the new table with new basic solution, we have to do a process. So this row is called pivot row. Okay, pivot row. So in order to get new pivot row, that is S2 is replaced by X2. So new basic variable, which is entering basic variables, is X2. So this is leaving. So S2 would be replaced by X2. Okay. And the new pivot row will become old pivot row divided by pivot element, and that is called the pivot element, which is the intersection of pivot column and pivot row. That is, in order to get new pivot row, we have to divide this pivot row by the pivot element. Okay, so let's see. When we divide 0 by 2, we have 0 here. When we divide 2 by 2, we have 1 here. We have 0, we have 1 over 2, and we have 0, and we have 12 over 2, which is 6. So this is new pivot row. So for rest of the rows, our target is to make all these elements, that is rest of the elements in pivot column, 0. Okay. So for this, we have to perform row operations, and that row operation will work like new row is equal to old row minus the coefficient of this row in pivot column times new pivot row. Okay, so let's try, and you will learn the process. New S1 row. So first of all, let's find out new S1 row. New S1 row. So let's follow the directions. Old row, that is old S1 row. Let me write that. 1, 0, 1, 0, 0, 4. This is the old S1 row. Minus, let me write minus here, the coefficient of this row in pivot column. Coefficient of this row in pivot column is 0. So let me write 0 here times the new pivot row. So this is the new pivot row. So let me write all the entries, corresponding entries. 0, 1, 0, half, 0, 6. And let's perform the computations. Let's see. 1 minus 0 is 1. 0 minus 1 is minus 1. 1 minus 0, sorry, 0 minus 0 is, since we are going to multiply every element with 0, so that will become 0. So pardon me for that. 0 minus 0 is 0. 1 minus 0 is 1. So this row will remain as it is in short. Okay. So let's write this. 1, 0, 1, 0, 0, 4. So our target was to actually make these elements 0. So we already had 0. So that is why this will remain 0. If you find some element in a row in pivot column 0, so you can write that row as it is. Okay. So this is what we learned from this. So let's find out the new row for S3. Okay. And again, follow the instructions. We have new S2 row is equal to old row. So let's write S3 row. Let's write old S3 row. So that is 3, 2, 0, 0, 1 and 18. And minus the pivot, the element in pivot column of this row is 2. So minus 2 times new pivot row, that is 0, 1, 0, half, 0, 6. Okay. So that will be 3 minus 0 is 3. Okay. And 2 minus 2 is 0. 0 minus 0 is 0. 0 minus 2 over 2, that is 1. 0 minus 1 is negative 1. And 1 minus 0 is again 1. And 18 minus 12 is 6. And I made a mistake here. That is 2 minus, no, that is okay. Okay, that is fine. So let's write this. 300 minus 116. Okay, I hope you understand the idea. Similarly, we can write 0. Let me write this for you. So we are going to do this iteration in detail so that you can understand the process, and that will be repeated again and again until we have an optimal table. So for 0, what we need to do, so let me extend this column. This is the pivot column including 0. Okay. So our target is to make this element 0. New old row is negative 3, negative 5, 0, 0, 0 and 0. And the element of this row in pivot column is negative 5, and we have minus, this minus, okay, times new pivot row 0, 1, 0, half, 0, 6. Okay, so let's again do the manipulations. So we have this result. Okay, negative 3, 0, 0, 5 by 2, 0, 30. Now again we have to check whether this is optimal or not, and we can see that we still have a negative coefficient in 0, so this is not an optimal solution. So in order to find out the optimal solution, we have to do the process once again. We have to decide entering variable, we have to decide leaving variable. So in this case, the only negative coefficient is the coefficient of x1 in 0. So that would be the entering variable of this table, and entering basic variable. And since this is entering basic variable, so we have to decide the leaving variable. One of the variables will leave the basic variables. So for this is the pivot column, and let's find out the ratios. So here we have 4 over 1, and here we have 6 over 0, and here we have 6 divided by 3. Okay, so the least positive one is this one. Okay, so S3 is going to leave this time. That is S3 will be replaced by this x1, and this is the pivot row. Again, we are going to do the same process. New pivot row will be the old pivot row divided by the pivot element, which is 3 in this case. So we are going to divide this each and every element by 3 in order to have a new pivot row. So let's do this. So this is the pivot row, pivot column, and this is pivot element. So new pivot row would be this one. That is this one. This was the entering variable. So S3 is replaced by x1. Okay. So I'm not going to get into details this time. You can go back and see the process and repeat the process in order to have this table. So finally, in this table, you can see that all the coefficients in 0 are either 0 or positive. That is non-negative. That is non-negative. So all the coefficients, that is entries in this in these columns. So all are non-negatives. So it means that we have achieved optimal solution. Now we cannot repeat this process again because there is no candidate of leaving variable. So our optimal solution would be z is equal to 36, x1 is equal to 2, x2 is equal to 6, s1 is equal to 2, and then s2 is equal to s2 is equal to 0, s3 is equal to 0. So the variables which are not present in the basic list are set to 0. They are non-basic variables, so that is why they are 0. So this is the optimal solution, and along with these values of variable, our optimal value function, objective function is 36. So let's have a look at the summary of simplex method. So first of all, we have to check the entry optimality condition. The entering variable, if the optimality condition is not satisfied, then entering variable in a maximization problem is the non-basic variable with most negative. In maximization problem, most negative coefficient, whereas in minimization problem, the non-basic variable with most positive coefficient in 0. And then we have to check we have to confirm the feasibility condition, and that is to decide leaving variable. And for this, both maximization and minimization problem, the condition is same. The leaving variable is basic variable associated with the smallest non-negative ratio with strictly positive denominator. Okay, so denominator should be positive. That is the entries in pivot column which are positive uh, contribute, right? So ties are broken arbitrarily if you find least positive ratio for two of the variable or more than one variable, then you can choose any of the variables as the leaving variable. So ties are broken arbitrarily, so randomly you can choose. And then we perform the Gauss-Jordan row operations. First of all, we have to identify the pivot row, replace the leaving variable in basic column with the entering variable. Then new pivot row becomes, by doing this, current pivot row divided by the pivot element. And then all other rows, including 0, are modified as new row is equal to current row minus its pivot column coefficient times new pivot row. So the optimum is reached at the iteration where all the z coefficients are non-negative when in case of maximization problem, and non-positive in case of minimization problem. So that is the stopping criteria. So I hope it will help you understand the basics of simplex method. So that's all for today. Take care. Bye.